Hello everybody! I hope everyone's having a wonderful day. So today I'm going to be doing a mathematics preamble. Now you might ask, Dan, what does this have to do with what I'm looking at? Well, this is mostly just meant to be a little review, or for those that aren't familiar with some of these topics, to just give you a little bit of a heads up of what these concepts are and some examples of how you can use them. So in this series, I'll be presenting about summations, series, and closed forms. And I'll also be doing a little bit on exponents, logarithms, and I'll be mostly focusing on methods of proof. Because oftentimes when we're interested in studying algorithms, it's very important we know a little bit about proving claims. So don't worry too much if some of these topics you're not familiar with before coming here, but you should have some familiarity with all of these topics to some extent. So the point of this is just to be a little bit of a primer, just so that gets you a little cozy with some of the things that you may say or encounter in one of my courses. So that being said, I'm going to just make a note that I will have timestamps on this video, just so that you can take a look at this. And if, say, there's one of these topics that you're interested in, you could skip right ahead to that, so you don't have to watch this whole thing. Okay? So that being said, we're going to get started. So let me just erase this. So the first concept we're going to look at are so-called summations. So let's talk a little bit about summations today. So I'm just going to make some notes. I encourage you to follow along. So often we encounter series given an infinite, I'll put that in parentheses, infinite or finite sequence. Terms of the sequence are added or multiplied together. So the way you got to look at this is I give you a bunch of terms that are going to be part of a sequence. So for example, the set of all even numbers, a sequence of those would be 0, 2, 4, 6, 8, 10, and so on if I wanted all the non-negative even numbers, for example. That's an example of a sequence. So in a series, we're going to be interested in where we have a sequence, and I'm looking at if all those terms are added together or multiplied together. Seems pretty nice and simple. So I'm going to talk about summations first. So given terms a sub 1, a sub 2, all the way up to a sub n. I'm going to assume this is a finite sequence, but it doesn't have to be. Their sum, which is what we would call a finite series, can be given by the summation which we'll denote with sigma. So sigma as follows. So I'm going to have sigma, and I'm going to have two numbers here. I'm going to have what we call this the lower limit, and we're going to have n here is going to be the upper limit. And we're going to denote this with a sub I. You can look at I like an index. And this is going to represent a sub 1 plus a sub 2 plus a sub 3 plus all the way up to summing over all of these to a sub n. So when you look at this, you should read it as the summation from I equals m to n of a sub I. So if you look at this lower limit, upper limit, you can think of, like, if you want an easy way of thinking about it, just think of it like a loop, where I'm going from m up to n, and I is the index, just like if you had on a for loop. So it's nice and intuitive and easy to understand. Okay, so that's what a summation looks like. So I'm just going to give you an example of what I mean by one of these. So just as an example, if I give you 1 plus 2 plus 3 plus all the way up to n, this would be the sum from I is equal to 1 to n of I. So notice that my I here is each one of the numbers from 1 all the way up to n. So notice it starts at 1, goes up to n. So often this series, by the odd chance, often is called the arithmetic series. Now, it's worth noting, just as another bit of terminology, if you're wondering what this is called, I said that this is a lower limit, that's the upper limit. This is often called the sum end. Sum end. It's a fancy word. Don't worry too much about the technicalities of these things. I'll give you another example. This time I'll give you an infinite series. So instead of just something that has a finite sequence of numbers, instead I'm going to go with an infinite series here. So here's another example. So here's just another example. So here's an infinite series. So I'm going to give you an example of an infinite series. The infinite series I'm going to talk about is so-called the harmonic series. This is another one, if you've taken an analysis course or a sequences and series course, you will have seen this at some point. Don't worry if you've never seen it before, that's fine. So it is the sum from k is equal to 1 to infinity. So that's how you know right away it's an infinite series. You see the infinity symbol there of 1 over k. So what does this mean? It means, so I read the k here, I put it in for 1, I get 1. When k becomes 2, then this is 1/2. Then when k is 3, this is a third. When k is 4, it's a quarter, and so on. And it's an infinite series. So there's an infinite number of terms here on the right-hand side. So this is just an example, just showing you an infinite series. Some of these actually have sums, some don't. I'm going to give you another example of another series, but I'm going to give you a version with a product instead of a sum. So I'll say similarly, a series that is a product of each term, we're going to use, instead of sigma, we're going to use capital pi, this big pi, is as follows. So here's just an example of if I wrote out a product. So I'm going to have a lower limit of 1. I'm going to have upper limit of n. And a sub I is the term right there. Now, it's worth noting that this is still a lower limit, that's an upper limit. But now instead of it being where I'm going to sum over them, I'm going to multiply over them. So the easy way you can remember this one, if you see the pi symbol, you think product. P product. Nice and simple. So this is a sub 1 times a sub 2, a sub 3, all the way up to a sub n. Nice and easy. So far I've just been covering notation. I'm just going to give you one example of applying this notation. So I'm going to let n be a natural number. So I'm just going to assume that that includes 0 just for our purposes. I'm going to define what is called factorial. I'm going to have n factorial, which is denoted by n with an exclamation mark like this, is the following. So I could define n factorial using this notation as follows. So you may have seen n factorial before, but let me write it out using this notation. So lower limit's 1, upper limit's n. It's going where the term here is going to be k. And I'm going to have n times n minus 1 times n minus 2, multiplying all the way down to 2 times 1. That's n factorial. So that's how you can define n factorial using just this product notation. Okay, so I think that's everything I have to say about the notation when it comes to summations and series, in particular when we multiply and sum. So let me just give you a couple, well, I'm going to give you a few properties of series. In particular, I believe I have all mine are involving, I got one with products. So let's take a look at that. Okay. So I'm going to give you some properties of summations. That S sort of melted in the microwave. And products. So I'm going to show you a bunch of neat little properties you can use. So I'm going to define, I'm going to say if a sub m plus 1 dot 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 and b sub m comma b sub m plus 1 dot 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 and so on are sequences. Remember, a sequence, think of it like all the odd numbers or all the even numbers, say non-negative ones. You have some starting point and you kind of go along and you have a sequence of numbers. Okay, are sequences of real numbers. So I'm going to keep this rather general. So we're going to be talking about real numbers here. So these can include your counting numbers, rational numbers like fractions. It also includes the rational numbers like square root of 2. And C is any real number then the following equalities hold. Whoop. One quantifier I want to add on here. For any n greater or equal to m. So I'm going to have these three properties I'm just going to list here. I'm just going to state them as fact as opposed to proving them for you, just because it's not going to be too important for us to prove these formally. But you should be able to convince yourself using algebra that these should hold. So I'm going to have a sum from k is equal to m to n of a sub k. And I'm going to have another sum. I'm going to sum these two summations here. So I have two summations, each with their own sums within them. They each have an own sum end. what I can do is I can actually lump them together like so. So if I have two separate sums like this, I can actually combine them into a single sum. Likewise, you can clearly see this is an equality, so I could decompose, or there's a fancy word for this. I'll let you think about it. What is it? Distribute. You can distribute over a summation like this. So if I have two terms I'm adding in a sum, I can distribute over a summation. So now I get two sums instead of just one complicated one. So that's a handy property to have. Just don't forget about this one. This one's really handy for algorithm analysis. So another one is if I have C times the sum from k is equal to m to n is actually equal to the sum from k is equal to m to n of C times a sub k. So another very handy property. Now I wrote it this way just so I want you to think about this. Remember this being an equality here. So oftentimes you'll encounter where you have some constant times something interacting with this kind of iterating variable here, this k here. So this might be some counter, like when we had our example with the 1 plus 2 plus 3 plus 4 all the way up to n. We might have like I times c. Notice that c has no relationship with the terms inside. So what happens is you can look at it as each term. So if you're not really convinced by this, write this out from, you can have a sub m plus 1, a sub m plus 2, and so on. And you'll notice each one's multiplied by c. So you can actually factor out the c from all of these terms, and you get what's here on the left-hand side. So isn't that handy? Third one, this is one involving products. So if I give you a product such as this, and I'm multiplying it by another product like this, it's going to be very similar to number one, except it's going to be carrying over multiplication. So it's going to have a product. Again, if you're not convinced by this, just write out what these series would be and rearrange terms using associativity. So you'll notice that now I can distribute over a product using this. So these are just a few properties I wanted to point out for you. So I'm going to talk a bit more now about closed forms. Now, very often, when we actually talk about analysis of algorithms, we very often need to have this nice thing of a so-called closed form formula or closed form. Sorry, closed form expression. I get a little excited here. Now, very often you'll notice these sums here, sometimes they have many terms to them. And I would like to have a nice simple formula that I can calculate using a constant number of operations to evaluate and determine the total sum over a summation like one of the ones we've seen. So that's the point of one of these closed form expressions, is that I can evaluate it using a constant number of operations, as opposed to having the sum over that whole thing, which isn't as pretty. Sometimes it exposes asymptotically the behavior of what the function that represents that sum looks like, at least from our context. So I'm going to talk about some common closed forms. So I talk about some common closed forms. A little high up there. Common closed forms. So it's worth noting that under normal circumstances, I would never expect you to memorize all of these, because they're very much, if you use them often, you'll remember them. But there's going to be a couple I'll point out here that I'll put a little star beside them that I would expect you, once you've used them a few times, you'll probably get pretty cozy using them. They should relate very closely to some of the things I've shown you previously. Another one I will not. However, I will prove it towards the end of this thing. If you watch all of the videos. So let me just list these out. So these are for your reference. So the sum from I is equal to 1 to n of I. So the arithmetic series, this is equal to n times n plus 1 over 2. At some point, I will give you a proof by mathematical induction to show you this one is in fact true. So this is the arithmetic series. This one I would expect you to pretty much remember after a while. Again, here's another one. Sum from I is equal to 1 to n of I squared. So this is just the squared term, so it's just I where I square it. This is equal to n times n plus 1 times 2n plus 1 all over 6. Looks, it's not as clean as the other one. This one should remind you a little bit of one of the properties I showed you over on the left side. Here's one I would expect you to usually remember. It's based on basic counting rules. So I'm going to assume A and B are integers. And I'm going to assume that C is just some real number. And that A is less than or equal to B. Then the sum of I is equal to A to B of C is equal to C times B minus A plus 1. Now, I'll give you some justification for this. So notice the lower limit here is A, the upper limit is B, and notice I'm summing over C's. So I'm going to have C plus C plus C plus C, but how many times is C going to occur? Well, it's actually going to be B minus A plus 1. Now you might ask where the plus 1 came from. It's actually because when you count an element in itself, you have to make sure you include the one that you, because when you take a, say if you have, let me just draw a little picture for you. Say for example, if I had like B was 5 and say A was equal to 2. So you'll know that it has to be 2, 3, 4, and 5. Now you would agree with me that B minus A is in fact 5 minus 2, which is equal to 3, right? But remember, there is at least one other element I haven't counted if I were to take all the terms. It's the lower limit that I didn't count for. Or it could be any one of the elements. The point is that if you actually want to count up the number of elements, the number of times I have to go through this, it's not that it's actually the subtraction of these two. It starts at 2, then 3, then 4, then 5. It includes one of them. You go, like I said, go back to the analogy of the for loop. You can think of it like where I have a my upper bound on my upper limit here is a less than or equal sign, not a less than sign. So I have to include the upper limit and my count, or lower limit, respectively. Okay, so that's where this comes from. Just think of it how many times you have to count all the elements. And this C, that's just actually from this property I showed you over here, the property number 2. Okay, let's go for another one. Property D, here's another one. If I give you a product, so I'm going to have lower limit is 1, upper limit is n. I'm going to have I times I plus 1. This is actually equal to n times n plus 1 times n plus 2 all over 3. I don't have any much interesting to say about this one. Now, I also do have a version of the arithmetic series in my list as well. That's number E, or item E. Instead, I'm going to skip right to F, and I'm going to put it over here. So let me put F here. This is the last one in my list. So I'm going to assume some real R not equal to 1. And I'm going to imagine I have the following finite series. Now it's worth noting that there is an infinite version of this where the upper limit is in fact infinity. So I'm going to imagine I have two numbers, L and U. And I'm going to have A times R to the I. Or remember, R is some real number that is not equal to 1. So this right here is in fact equal to a times r raised to the L minus r to the u plus 1 all over 1 minus r. Now remember, that's a capital L right there. It's not a 1. You might know this one. This is called the finite geometric series. Every once in a while you will run into this one. You will be warned. It sometimes pops up. So those are all the interesting ones I really wanted to point out. I'm going to point out a couple tricks that you could do with summations, just to give you a couple tricks. Because I just want to make sure that, because when you're manipulating summations, sometimes it's a little unclear what you could do with summations. Especially when you just see some daunting looking thing and you're like, okay, well, how can I simplify that down? Because oftentimes the goal is to get a closed form. So that you could say something about, say, a running time of an algorithm. Okay. So I'm going to give you some tips on how you can do. So I'm going to call this simplifying summations. We'll call it simplifying summations. Simplifying summations. So I'm going to give you some tips. So you can think of these as common tricks you could deal with summations. So the first one I have is, and this one should remind you of the first tip I gave you. Multiple terms inside a summation. Can be distributed. Remember, that's that fancy word. Distributed into multiple that I sort of melted there. Multiple summations. So what we're going to do is, the tip is, if you see a very complicated summation, distribute it into a bunch of smaller summations if you're not sure what to do with it. Just as an example, imagine I give you the sum from I is equal to 1 to k of I minus 1. Now, because of property 1 that I showed you in my list of properties, you know that you could split across this summation, because really you could look at this as plus negative 1. And bam, now I have two summations. I is equal to 1 to k of I minus the sum from I is equal to 1 to k of 1. And now I already know what this looks like. I know what this looks like. These both look like ones in my list. Let me just remind you. Let's go back over to my list here. So I have actually both of these summations. They look like things that I've already shown you. So let me just get to go a little bit further over there. Just a little further. Okay. That's good enough. Okay. Note, does this look a lot like the first summation? And this one looks a lot like the second one, right? So let's go back over here and let's apply those closed forms to these simplified summations. So let's see what we could do. So notice that I have this I here. The upper limit is k. So I can write this as k times k plus 1 all over 2. So that one deals with this first sum. The second one here is just like our one we had before. What we need to do is look at this. You can think of the c as 1. So I have 1 times something. What was the something? It was upper limit minus lower limit plus 1. You want to count up how many times the 1 is getting added. So it happens how many times? K minus 1 plus 1, which makes sense because it should occur k times. Because it's 1, then 2, then 3, then 4, then 5, which is all the way up to k, which is k times. So I have minus k minus 1 plus 1. This is just k, right? Then I can simplify this a little further. So I'm just going to make this a little easier to play around with, I'm going to make a common denominator across these two. So I'm going to have 2 like this. So I'm going to multiply this by 2 so it has a common denominator. So I'm going to have k squared, because this will be k squared here. So it's k squared times, sorry, it's k times 1, which is k, right? So I have k squared plus k, and this is just k here, so it's minus k, but now I have to multiply it by 2 to make it a common denominator. So it's minus 2k. But what's this? What's this? What's this? This is just k squared minus k, because remember it's k minus 2k, that's minus k. Because I'm only left with 1k left, right? And I subtract, that's all over 2. And bam, I can factor out the k here. I got k times k minus 1 all over 2. See, it's not too hard. It's not hard. Is that nice? So if you see a summation, you're not sure what to do with it, and it's a sum like this, try breaking it apart into simpler sums. That's my first tip. My second tip is that sometimes it is good. I don't like using the word good because good and bad are subjective terms. Sometimes it is good to write out what the summation means, then group related terms. So then group terms. Just as an example, I'm going to show you something that looks really complicated, but with a small little bit of hindsight, we can actually make it look really simple. Okay. So I'm going to have the sum from I is equal to 1 to 400. Well, it's so far a little daunting. I'm going to have minus 1 raised to the I plus 1 times I over 2. Now, these symbols here, if you've never seen them before, those are ceiling. That means ceiling of I over 2. This means round up to the next integer if it's a fractional part. Likewise, there also exists this thing called the floor. Looks like this. It means round down. So if I have a fractional number and I see the floor, I round down. If I see the ceiling, I round up. Okay, so this looks a little bit daunting here, but let's just write out what it says. So let's see what this says. So I start off with 1, and I see minus 1 raised to the 1 plus 1. So it's minus 1 squared. If you may remember, if I have something like minus 1 squared, if I take the square of a negative number like that, I should end up with what? I should end up with a positive number. And whenever it's odd, it should be negative, right? It flips the parity. Flips from positive, negative. Well, technically not parity, the sign. We'll see an example much later on where we're dealing with parities. Anyways, so if I write this out, I'll let you think about it. It's 1 minus 1 plus 2 minus 2 plus 3 minus 3 plus 4 minus 4 plus all the way up to plus 200 minus 200. So do you see what's happening now? If you actually look at this and you try out each one of the terms for a little while, you start seeing the pattern. Notice that I'm adding a term, then I take it away. I add it and I take it away. And I add it and take it away. So if I rewrite out this sum, you'll notice that I'm going to have a bunch of positive terms. So these are all my positive terms. Then these are all my negative terms. And now I know what to do with each one of these sums, right? Now if you already knew the hindsight here, you know right away the result, but I'm just writing it out just so you can see how I manipulate the summations, okay? You'd probably be able to look at this and be like, okay, I already know the answer, but I just want to show you how I manipulate the summations, because it may not necessarily be the case that these are 200s. You might use this idea somewhere else. So this would be 200 times 200 plus 1 all over 2. Remember, that's just a closed form that I'm applying. Let's do the exact same thing. Minus 200 times 200 plus 1 all over 2. This is equal to 0, right? Because I add the term, then I take it away every single time. And why is that true? It's due to symmetry. Every single time I have all my positive terms are actually equal to all the terms I'm taking away. So so by symmetry, they cancel each other out. Okay? So that's another trick I can give you. So I'm going to give you two more. Okay, so the next one I'm going to do with you is the one that you should get used to if you get something that doesn't look as pretty and something the thing you really want. Because oftentimes I'll have summations. You notice all the ones I gave in this example, they all looked really nice and easy to apply the closed form expressions, right? Well, sometimes you get things that don't quite fit the mold, but you can easily modify them to get something that looks like it. So you can add or remove terms. So I can add or remove terms to, in quotation marks, massage the summation into a closed form that is known. That's all I'm going to do, is I'm just going to take and add and remove terms. So I'm going to massage the summation so that I could pop something in or push something out, so I could get something that looks like something I would like to have for my closed form expression. So here's just an example. It's nice and simple, but it should give you the idea pretty quickly. So imagine I give you a sum with the lower limit is 3. So from I is equal to 3 to k of I. Now, if you've seen this, you know, okay, I know what this looks like when I is equal to 1, right? But I don't know what it looks like when I is equal to 3. So what am I going to do? I'm going to try to make it look like I is equal to 1 by doing something else. So remember, this is 3 plus 4 plus 5 plus all the way up to plus k. Now, to get the thing I would like this to look like, it's 1 plus 2 plus 3. So notice that I need those 2 extra terms I need to put in there somewhere. So notice that this is in fact equal, if I massage this. Now, besides, massage is not really a formal term. I just like to use it because it gives you the idea of what I'm going to do. So I have the sum like this. And I'm going to subtract off those 2 extra terms that I was trying to massage by introducing them. So by introducing them here and getting rid of them after, I can get something that looks like something I can work with. But what's this? That's k times k plus 1 all over 2. What's this? That's 1 plus 2. That's equal to 3. Boom. Isn't that nice? So just think about it. If you see a form that looks like something you want, a very powerful and simple idea is all you need. Massage the summation. Okay, now this one is, I would consider, the more technical of these 4 techniques. And I guarantee you, if you've taken a class where you had to see summations before, somebody would have shown you this trick. I'm personally not the biggest fan of it, but it's very powerful in its own right. It's not very powerful in the sense compared to some of these other techniques. So modifying the lower and upper limits to obtain a known closed form. So just like in my previous example here, notice I started off with I is equal to 3. It'd be nice if that was equal to 1, right? Now, what I would like to do is I would like to be able to change what these upper and lower limits look like so I can manipulate it like it looks like the form I would like it to look like. So here I'm going to give you an example. Some choo-choo time. So assume k is greater than or equal to 2. I'm going to let g of k equal the sum from I is equal to 3 to k plus 1 of 2y plus 2. Now, if I showed you this right off the hoot, there are several things you could try to do, right? You could try this third technique here. You try to massage the summation. That would work. I'm going to try something else here. I'm going to try to manipulate the upper and lower limits of this sum so it looks like something I could easily manipulate using the first trick I did. So I would like to make this into a 1. I'm going to let j, so I'm going to assume another variable called j, and I'm going to make it equal to I minus 2. Now you might ask, Dan, why are you picking I minus 2? Remember, I want to make I equal to, I want to make this 1 here. So what I would like to do is I would like to take 2 off of it. That's where it's coming from. So update the lower and upper limits and inside careful. The inside part is most important. Oftentimes students will forget to update the inside, the summand. That will cause a lot of problems down the line. You'll get an incorrect sum, most likely. So what's the lower limit? If I want to make it so that I can use, let me think. I would like to make it so that j, because I'm going to introduce j as now the lower limit, this variable. So I want to make that look like 1. So I'm going to say the lower limit that m sort of mutated there. The lower limit is j is equal to 3 minus 2, which equals 1. So you'll notice that the difference here, I'm going to try to put j there, but by knocking everything down by 2, I have to do that everywhere. But when I bump things down, it actually causes another effect inside the sum. So let me take a look at that. So j is equal to 1 there. The upper limit. So remember, I knocked down the lower limit by 2, so the upper limit also has to get knocked down by 2. Becomes k plus 1. Remember, that's what the original upper limit is. I'm going to subtract 2 from it and end up with k minus 1. Why do we need to have it so we update both of these? It's because we need to make sure that there's the exact same number of terms I'm summing. However, we have to be careful because now I'm going to put everything in terms of j instead of I. Now, I bumped everything down by 2. But what happens inside? And the summand becomes what? Well, remember, it's 2i plus 2. Now, wherever I see I want to put j's. But what's j? Well, if you rearrange this equation here, I would need to add 2 to both sides of this, so it's I equals something over here. So when I bumped everything down by 2, what actually happens is I actually add 2 to the sum end inside. So if you're not convinced, just take j is equal to I minus 2, rearrange that so it's in terms of I. So we have I is equal to j plus 2. Just add both sides to the equation there. So you get this, which is going to be equal to 2 times j plus 2 plus 2. And this is through rearranging on that equation over there. So what do we do? Well, let me just make some more room here. So I'm going to just substitute now in j instead of I, and I'll have a brand new summation. If you're wondering, the name of this technique is substitution. I'm just substituting one variable for another. So through substitution, we obtain that now we obtain this new sum. J is equal to 1 to k minus 1. Remember, this is the updated lower limit. That's the updated upper limit. And then I have 2 times j plus 2 plus 2. The sum end has been updated. If you do some algebra, you'll end up with this being j is equal to 1 to k minus 1 of 2j plus 6. And now at this point, you can apply the techniques that you'd seen previously. So I encourage you to try the other techniques. Try the other techs to finish this. So notice that now I have something that I can easily apply I could distribute that into two sums and simplify it and the way I did it before. Is that nice? So this fourth technique is really handy if you have very complicated sums. So sums that just do not play nice with you. And it's really unclear what you can do with it. So that's all I have to really say about summations. It's worth noting that when you have a double summation, one point of contact you should really be careful on is you have two sums. Like if you give you two sums that look like this and you have some term right here, it's worth noting that the sum here and the sum here, you can switch the summations around. Sometimes that's handy to do. Another thing worth noting is that if you're summing over them, you got to think sort of like the intuition I really like of nested for loops. So if I'm summing over this, if there's a variable that's related to if there's something over here, think of this like the outer loop, this is the inner loop. Let's say this was I and this is j. If j relates with I, like say the upper limit of this is, say I. Sorry, I'm getting really excited here. That you have to be really careful because you got to look at I like a constant inside here, like you're evaluating this sum. Hopefully I'm clear. So you can give that a try if you're curious about it. Feel free to ask me any questions about that if you'd like. Anyways, I'm going to transition over to talk about exponents. So let me just erase the board here, and we're going to talk about exponents. So hopefully you found these summations pretty handy. Okay, so let's talk about exponents. Okay, so I'm going to talk about exponents with you. I'm going to assume that you know a little bit about exponents and have seen them before. But I'm just going to remind you of properties that exponents have, and we'll see some examples. So for any real number, x not equal to 0, and power or exponent n, which is going to be a real number. This fancy r here, that means real number. We write x to the n, where x is the base of the exponent. Is the base of the exponent. And x to the n is read as follows. So you could read it in a couple different ways. You could read this as x to the power of n. You may also read this as x raised to the exponent or power n. Now, exponents really, when you deal with general real numbers, at first it's really kind of unintuitive what you do with them. I like to think of them like in terms of integers, because that's often what you're going to encounter. Intuitively, see, I did it. Intuitively, when exponent n is an integer, then you could think, then x to the n is equal to x times x times x times all products of x, and this is done n times. So you could just think of it like a repeated multiplication. That very much, when you think about it as repeated multiplication like this, it's very intuitive, and a lot of properties about exponents make a lot more sense when you want to first convince yourself of things. It's, as a remark, also, it's worth noting that we consider x to the 0, or the 0th power. This is equal to 1. And if ever I give you a negative exponent, like x raised to the minus n, this minus is just saying it's 1 over that thing with the exponent. Okay? So I'm going to give you some properties, and we're going to do some examples. So let's look at some properties. So let's talk about some properties that exponents have. So I'm going to let real numbers x and y not equal 0, and m and n be real numbers. So I'm going to assume these guys here, and let's proceed. So the first one I'm going to talk about is the product property. So a product property, quite simple. If I have two numbers that have the same base, but they're raised to different exponents, I could do the following thing. So if I have x raised to the m and x raised to the n, notice the same base on the exponents. If I have the same base, then I can sum over them. So if I have a product like this, the exponents add to one another like this. Just as an example, if I have 2 cubed times 2 squared, what should that be? 2 cubed times 2 squared. Well, by this product property, it should say that it's equal to what? It's equal to 2 to the power of 3 plus 2, which is 2 to the power of what? 2 to the power 5. What's 2 to the power 5? Anybody that knows powers of 2's? Let's see. 2. So 2 to the power 1 is 2. 2 squared, 4. 2 cubed, 8. 2 to the 4, 16. 2 to the 5, 32. Sure, if you're interested in computer science, you probably know your powers of 2 back of your hand, you know? Slap! Hey, okay, so that's the product property. Let's talk about some more properties that exponents have. Okay, so the next one is the quotient property. If you're not sure what the word quotient means, it means you can think of it as division. Whoops, not quotient rule, quotient property. I'm getting ahead of myself. So I have the quotient property. Now, if you could see that in a product, it adds the exponents, you might guess what the quotient would do. So if I have x raised to the m over x raised to the n, what should happen? Well, it should be that it subtracts them. So it becomes a difference. Instead of a sum, it's a difference. So, just as an example, just again, because I like to be complete with you, is I give you 2 to the power of 10 over 2 to the power of 7. That's equal to 2 to the power of 10 minus 7, right? And that's 2 cubed, which I'm sure you know that that's equal to 8. Okay, another property. Now, this is where things are going to get a little bit fun. These ones I consider more interesting properties. I promise you, you will find these pretty interesting at some point. If you're doing some fancy algorithm analysis, every once in a while, some strange thing pops out where you're like, oh, well, why would I ever need this property? Sometimes it creeps into your analysis every once in a blue moon. This is one of them. Okay, so if I give you x raised to the m, and I have all of this. Now remember, this is in parentheses. And if this is all raised to the n, this is equal to x raised to the product of m and n. So it's not a sum like this. It's because it's being raised again to another power. So just as an example, if I have 2 to the power, so I have 2 squared like this, raised to another power of 5 like that, then this is 2 to the power of 2 times 5, which is 2 to the power of 10. Now for your pros that know all your powers of 2, I'm sure you just know that this is going to be 1024. Bam, bam. You see? See, I'm getting really excited here. Okay, another one. Power of a product property. So power of a product property. So this is one that it oftentimes doesn't get enough love, and sometimes it does pop up in some of the proofs if you're trying to prove some of these properties. So let me show you what this is. This is quite simply stated as follows. So if I have x times y like this, so just a product, and I raise this to the power of m, it actually decomposes over the product here. So it becomes x to the m times y to the m. Now, one thing I must point out is remember that these do not have the same base. So notice this isn't the exact same as the product property I had over there. This is in fact a little different. So just as an example, if I have 3 times 2 squared, all squared, this is just 3 squared times 2 squared, which is just 9 times 4, which is equal to 36. Bam. Now, you might ask, Dan, how do I know that that property makes any sense? Well, think about it. If this is x, so I want you to first think about if the power was an integer. It's going to be x times y times x times y times x times y. How many times? M times. So if you think about it more like that, you can actually rearrange all the powers that you have. So how many times do you multiply x? You multiply it m times. How many times do you multiply y? M times. See? Nice and easy. Okay. Believe it or not, that's all I have to really say about exponents. So hopefully you had a little bit of fun with this. So we're going to move on to talking about its cousin, its inverse, the so-called logarithms. So let's talk about logarithms. So let's talk about logarithms, okay? Let's talk about logarithms. So I'm going to define first what a logarithm is. Let there be positive real numbers b, x, and y, where b is not equal to 1. So it's worth noting that exponentiation and logarithms are very closely related. So we write b to the y is equal to x if and only if, now just as a reminder, if and only if you read something on this side, whatever I write over here, they are going to be logically equivalent. As in, if this is the case, then this is the case. If that's not the case, then this isn't the case. Clear? Okay, so so if I have these right here, if and only if, I'm going to write it as log base b of x is equal to y. So this right here is called the base of the logarithm. And I'll give you a very basic intuition of why exactly you might find this definition a little strange at first. And then it actually makes a little more sense. Okay, so imagine I give you the base of exponent, hence the b, base of the exponent. Get it? Get it? So base of that. Okay, you want to think about it more like a game. So if I have b to the y is equal to x, I want you to imagine I give you x. I give you x right here, and I tell you the base of my exponent. I want to know what power you raised b to get x. So it's in fact the inverse of exponentiation. So in this, I raised the power of y to get x. Here, I have b, and I have the result of b to the y. I want to know what exponent you raised it to. So these are closely related. If you know one of them, then you know the other one. So very often, knowing this, so oftentimes you'll find that this definition of the logarithm will sometimes creep into things you're doing where it's very unclear, like, okay, I have this logarithmic term. What does that mean? Well, remember, this is the definition of a logarithm. Okay? So actually, just to make sure I'm really clear what I mean by this, let me just do a quick example. So imagine I give you 2 cubed. What is 2 cubed? We already established that's 8, right? What is that in the logarithm world? Well, the base of the exponent is 2, so it's log base 2. And what's x? X is the result here. Log base 2 of 8. Well, think about it. Remember, what is the exponent I raised 2 to get 8? It's 3, right? Notice that it's really not that tough. At first, it's a little strange when you look at it because Okay, well, I'm not used to thinking about things backwards like that. It's because it's an inverse operation. So that being said, when you think of an exponent, it shoots up like this. However, a logarithm does, instead of shooting up like this, it curves like this, but it curves slowly. So oftentimes when we do like algorithm analysis, sometimes you find that if you kind of come across an algorithm that has logarithmic properties, like that look like something more like this, where it's like where n, like the input, has something to do with it. Usually that's a desirable characteristic of a running time of an algorithm, because the growth rate of such a function is very slow. So this is in contrast to something like a linear term. Okay, so let me make some notes here. So logarithms have different bases. As you can clearly see, I can pick what the base is. So some common bases include the following. So here are some common bases. So the first one I want to mention is that is base E. You might know this constant. This is approximately equal to 2.71828. If my memory serves me correctly, I'm trying to do this off the top of my head. So whether it's E, you might know this constant. You might know this as if we have this base, it's often known as the natural logarithm. Sometimes written as ln of n, where n is the input. Another common one is the base 2. This one's very common in computer science circles. Oftentimes when you talk to computer scientists, if they just write log n like this, they're often assuming that it's log base 2 of n. Not always, but very often. In general circles, you'll often will find that they assume base 10. But in computer science circles, usually we'll find that people tend to assume the binary logarithm. So this is often called the binary logarithm. Oftentimes, this logarithm sort of melted in the microwave again. Oops. So this is called the binary logarithm, and I'll say it's common in computer science. Oftentimes pops up in algorithm analysis all over the place, whether it be talking about representations of information like bits or information theory, all sorts of fun things, like even ranging from wild things like entropy. So I want to remark, just because I like to bring up things that aren't as common, some people use the notation LB of n. I don't see it very often, but I feel like I need to mention it. So you won't find me usually using that notation, but I feel like I need to acknowledge that it exists out there. So you ever see LB of n? That usually is the binary logarithm. But just you won't see me using it very often. So I'm going to talk about some properties of logarithms. Now, you're going to find I'm not going to do a lot of examples with these because you will see plenty if you start playing around with logarithms. And that, like I said, logarithms and exponents are closely related. Hence, you're going to find that all the examples I gave, I encourage you to try them with logarithms. So let's talk about properties of logarithms. Sorry, I'm getting really excited here. I'm just waiting for it to kind of scoot over. There we go. So here's some properties. Here's some properties of logarithms. So the first one is the so-called product rule of logarithms. So you're going to find that there's going to be a natural analogy to almost everything I've shown you before. Almost everything. So if I give you log base b of x times y, so a product like this, what happened when I had my exponents? When I thought about exponents where I had x to the m times x to the n, what happened? The exponents added to each other, right? But remember, in a logarithm, what are we talking about when we talk about what log base 2 of something is? It's the exponent, right? So it's quite natural that the outcome of this should be that they add to one another. So you could split a product into two sums. Is that nice? Naturally, think of a quotient rule as you might guess it. I'll let you think about it. Is it going to be that it adds them, or it's a difference? It's a difference. So we have log base b of x over y. This should be, instead of a sum, it is a difference. Not a plus, a minus. Okay, so we have the quotient rule. Now, intuitively, I told you that the product rule is where I add over products. So imagine I had a bunch of products over each other over and over again, like an exponent. Just like imagine if it was an integer power. What should happen? I should have a bunch of sums, right? And if I have a bunch of sums that look exactly the same, I can factor them into some term. So for example, if I had a power of 3, like say if I had 3 terms here, you would agree with I have three terms in a sum, right? Well, this is going to be a nice generalization of that. It's called the power rule of logarithms. So if I give you log base b of x to the y, you could drag this y out in front, and then I end up with log base b of x. So it's going to be y times log base b of x. It's worth noting, remember, these are all equalities, so you can rearrange them back and forth. So if you really don't like a constant in front of your logarithm, you can drag it up as an exponent, and vice versa. So keep that in mind. Finally, one last one I need to point out is the change of base formula. So suppose you have a logarithm and you really don't like the base of your logarithm. You want it to look like something else. Like say if you have something that's in base 10 and you want to convert it to base 2. There is actually a nice relationship that logarithms have, so you could switch the base. So if I give you two valid bases, a and b, log base a of x is equal to log base b of x over log base b of a. So if I want to convert from a to b, notice I introduced this constant term right here. So notice they differ by a constant. You'll find that the power rule and the change of base formula tend to be very often something that will creep into big O proofs, for example, when it comes to dealing with logarithms. I find generally these two are the ones you're going to run into very often. Not often, but all these sort of have their own part to play. But I find that these two tend to be your best friend when you're dealing with logarithms and those types of analytical proofs. Okay, so that's all I have to really say about logarithms. Bam! Isn't that nice? So what we're going to do next is we're going to move on to talk about methods of proof. So let's talk about different proof techniques. So let me just erase the board. Let me move on back over there. Okay. Let me just find out where I am. Okay. Let's talk about methods of proof. Now, just as a remark, I'm not going to be talking about elementary forms of logic per se. So I'm not going to be talking about propositional logic here or other types of classic logics. I'll just sort of assume a general understanding of how logic works. And a lot of the big ideas I'm going to show you should make clear sense. They aren't going to be something that's going to come out of left field. At first, if you've never seen these ideas, you probably should have at some point. If not, sit back and just enjoy the fun, okay? Everybody's welcome here. So, there are two main kinds of mathematical statements that I want you to be aware of. So, mathematical statements of truth are quantified by universal. Now, if you're not familiar with what the word universal means, just think of it as for every, or for all. So if you ever see statements like that, I'm talking about universal, universal, and existential. So these are things like there exists, or there's at least one. That's very often when you see existential. As existential quantifiers. So if I give you some statement, which will be either true or false, they'll be quantified by things like universal and existential quantifiers. So words that look like these, which do have symbolic counterparts, but you might see them a little later on. I'm not quite sure. Which form the basis of proof writing and mathematical arguments. So just something I want you to keep in mind, just to remind you of what these words might mean in this context. When somebody sort of melted, that somebody writes for all x in D, this means in, this symbol here, means in, where D is some collection, example, a set, then say X has a property. Say X has a property. That property is true for all X in D, or for every, whichever you'd like to phrase it like that. That's what universal, whenever you see somebody says for all, a universal statement. When somebody writes for some, notice the change of language here, for some X in D, and says X has property, has some property. I'm being kind of open-ended here. Has some property. It doesn't mean that every one of the x's in D have this property. It means at least one x of d has the property. You know it exists, hence the existential part of this. So it means it exists. So that's universal, that's existential. Now, I want to point out something that's very important. It's going to come up later. The logical negation of a universal statement is an existential statement. And vice versa. So that's something I really want you to really pay attention to. Now, I have it here in my notes, but I'm just going to kind of walk you through this idea. Okay, so if I imagine I give you a universal statement, and I tell you it's false, how would you tell me that it's false? What would you do? Now, at first sight, what you would tell me is that if I told you that every one of my friends is wearing a red shirt, and I told you no, one of your friends isn't wearing a red shirt, right? That's naturally what you would say to somebody if somebody declared that all your friends were wearing a red shirt, just as an example. Right? But what does that mean? It means if I can point out a friend of yours that isn't wearing a red shirt, would you agree with me that that's an existential statement, right? It means that there's at least one of them that doesn't have the property. But what is not having a property? It's a property, right? So that's why if I want to negate a universal statement, I end up with existential statement. And likewise, if I have an existential statement, I say there's at least one object with a property. Say I have one of my friends that at least one of them's wearing a red shirt. What would you need to do to show me that there is nobody with a red shirt? I would check each one of them and tell you that no, there isn't such a thing, right? But what is that? That's a universal statement. But what is the universal statement? It's me saying, for every one of my friends, all of them aren't wearing red shirts, right? That's why the logical negation of a universal statement is an existential one and vice versa. Is that clear? So when you give me a universal statement and I say, like, no, yours is wrong, and you present a negation of that, it isn't another universal statement, at least when we talk about a single quantifier like this. You can build more complicated statements with quantifiers like these, and in combination, when you negate one, it flips the quantifiers from universal to existential, and vice versa. But notice that the property, in fact, flips as well. I'll let you think about that. I just want to keep things at high level here. So don't worry if that seemed a little bit daunting. I'm not going to go full-blown symbolic with this. I just want to give you the intuition. Keep things nice and simple. So in your studies, you will encounter probably multiple quantifiers. For example, if we're looking at, say, big O notation, you'll encounter existential statements with multiple quantifiers. But once you understand what the quantifiers mean, it's really not that bad. Okay. So I'm going to talk about a variety of different approaches you can to prove claims. So I just want to give you a flavor for what kind of statements usually mathematicians and computer scientists and other people that are interested in mathematical statements tend to make so that I could talk about different kinds of proofs. So I'm not going to talk about every single type of proof out there. That's just not happening. Instead, what I'm going to do is I'm going to kind of categorize different styles of proofs. First, I'm going to talk about direct proof. I'll spend a little bit of time with this. So many claims that people make are universal claims. So many claims made are universal statements. Now, there are some standard ways you can prove universal statements. There are standard ways to prove such claims. So the first one, and this is one that you first encounter if you're studying logic, you'll encounter them in the form of truth tables and checking if forms are valid or invalid. You may have encountered this before, you may not, if that's okay. It's called the method of exhaustion. Or at least I'll call it that, because it's very intuitive. What you do is you consider all possible cases, then prove that, then something's wrong with that, then prove each case is true, or break the statement into cases. And then, of course, with each one of these cases, you would prove each is true. And prove each true. So you might naturally say, Dan, the method of exhaustion, imagine I give you some statement over a domain. That's what D is. If I'm talking about D, sometimes people call that the domain of interest or concern, or discourse, the domain of discourse sometimes. It's just, think of domain. It's like a set of numbers, for example, or if I give you some structure like a graph or some other mathematical object, I'm referring to something like a set. It could be, it's some sort of collection or something of that nature. Anyways, the thing that I would like to talk about here is that notice that the method of exhaustion, the first flavor of it requires me to be able to enumerate all of them, which doesn't seem very clear how to do that if you have an infinite number of them. Now, there's maybe some ways you can do that. I'm not going to focus on those, but you might know quite clearly if you're talking about basic forms of logic, like if you're talking about operators such as over truth tables, those will have, say, for example, exponential numbers of statements that you will check each one, and you can evaluate them based on truth values. So this would be an example of a method of exhaustion. If you want to check or prove that a certain logical form is valid, you would exhaust all possible cases of truth assignments and you would check them. That's an example of method of exhaustion. But you'll notice that I can do this over a finite formula of logic. Now, this may not, it's generally a technique that only has its reservations for certain things. The second part here is actually the one that's more interesting, at least in my opinion, is that I give you a statement and I can see that I can break or decompose the statement into multiple cases, and then I could prove each case separately. And if I cover all of my bounds on each case, so if I break it and I split all of my cases into two, like I have a domain, for example, if it was a domain on integers, say positive integers, every positive integer is either even or odd. If you think about it, you can prove this if you like. We're actually going to do something quite like that in a moment. You would agree with me that that's a possibility, right? Well, there's two possible cases there. If I show them for even and then I show them for odd, I've shown them for all the integers, right? That's a good example of this. Okay? So that's a proof by cases or division of cases. The other one, and this is the one that you're going to find very often when we deal with direct proof, is suppose an arbitrarily chosen arbitrarily chosen x in D, like above, like over there. And it satisfies the property. So your idea is that I give you x and D, and your job is to then prove it has the property, but you can't make any special assumptions about x. It has to be any one of the x's in D. Okay? So you would start off by supposing you have one of these, and your job is to deduce that x has the property. Sorry, I'm getting really excited here. So the big summary point I want to make is that in a direct proof, so this isn't a part of the second bullet, but it's closely related. In a direct proof, the idea is to show the property claimed to be true. Property claimed is true using previously established results. Previously established results and or observations that can be made via rules of logical inference. That N on that inference is a little funky. So the big thing here is that you either have a claim that you already proven before, or you deduce more things from logical inference based on what you're given. So you might observe a certain property that occurs for the thing you're trying to prove. This is very often the case when you deal with algorithms, for example. You might observe a property that the algorithm has. You might prove this property, and you might use it to prove something else. So that being said, I'm going to give some examples of some proofs. So let's do that. Okay. So first I'm going to prove an existential claim. You'll find that they're not going to be as interesting for at least this example, because I got to keep things simple. But I assure you that not every existential claim will be dead easy, but these ones will. Okay. So here's a claim. So I'm going to present a claim. Now, if this claim is true, we often call these theorems. If it's a theorem that is building to a larger one, we often call them lemmas. And if it's a theorem that comes as a direct consequence of a theorem, we call it a corollary. But I'll just call them claims here to keep it simple. Some people call these propositions, and that's fine too. So this is just an example of an existential claim I'm going to prove for you. Just going to show you how I can do a direct proof. So I'm going to say there exists. There's the keyword that you will see right away. That's an existential claim. There exists an even integer, n, such that it is the sum of two distinct prime numbers. So two distinct prime numbers. Now, just to discern everything for you, just in case you're not familiar with what an even number is, nor a prime number. An even number is an integer that can be written in the form of 2 times some other integer. A prime number has exactly two divisors, 1 and itself, where itself is another number that isn't 1. So something like 2, for example, is a prime number because its divisors are 1 and 2. 3 is another prime number. 5 is a prime number as well. Is 4 a prime number? No, because its divisors are 1, 2, and 4. Okay? Is 1 a prime number? No. It only has one divisor. 1. Okay, so let's prove this claim. Now remember what I said earlier. It's an existential claim. So it's a there exists, that means there's at least one. So all I have to do is show you that. So what's the game plan here? So I like to use the phrase the game plan because I like to think about the strategy for proving the claim. So I need to say what I'm going to do. So what would I need to do? I need to show you, all I have to do for this is show you one even integer that has this property, right? So I gave you an even integer, you have to show me it has the property. So I'm going to let n equal 10, for example. And now I have to justify for you that this, in fact, is a prime number. Actually, no, it's not a prime number, right? Got to read this carefully. It's the sum of two distinct prime numbers. But what does that mean? It means that there are two different prime numbers, and when I add them, I get 10. That's my goal here. I just decided on 10. You might find another number that works for this, but I just decided on 10. Then observe that 10 is equal to 3 plus 7, where 3 and 7 are prime numbers. And 10 is even, as 10 is equal to 2 times 5. Remember, it's 2 times some other integer. Now I have to give a conclusion. Therefore, there exists such an n so that it is the sum of two distinct prime numbers. And I'm going to indicate the end of my proof with this box. This just tells me that I'm done demonstrating the claim. So if you ever see a box like that, that's what it means. it's marking the end of a proof. It means I've demonstrated the claim. I've set out the proof. Okay, so that's one example there. Let's do another example. So that was an existential claim. Let's do a universal claim. So we're going to prove a universal claim. I'm going to consider two integers, m and n. Now, z here, you can think of that as integer. So if you see the fancy blackboard z, that means integer. If both m and n are even, then m plus n is even. So that's what we're going to prove. So if I give you two even integers, then the sum of them is also going to be even. That's what I'm going to prove for you. So remember what I said? We're going to do number 2. So I'm going to suppose an arbitrarily chosen element of D. Now, remember I have two numbers, so I'm going to arbitrarily assume m and n as even integers. So I'm just going to suppose m and n are even integer, are any, getting really excited here, are any even integers. Are any even integers. So what does that mean? Now, I want to show you a very powerful but important trick that you should be aware of from logic. It's called the existential instantiation. It's a fancy word for basically me saying if there exists an existential quantifier within a definition, you can invoke that and give it a name. So if something has that property and it exists, you can give it a name. So that's the fancy name for existential instantiation. Fancy word. Fancy word. So, well, m and n are even. So there exists, so I'm going to give them names because they exist, right? I told you, remember, even numbers, what are they? They are integers of the form 2 times another integer. So that means that other integer has to exist, right? So I'm going to give that integer a name, the one that multiplied by 2. So there exists integers k and k prime such that m is equal to 2 times k and n is equal to 2 times k prime. So now watch this, watch this. All I need to do now is I need to just write them in a form that's really nice, right? Then, well, what does it mean if I add m and n? M plus n is equal to what? I'm going to substitute m and n for 2k and 2k prime, right? So I have 2k plus 2k prime, right? But what is that equal to? And 2k plus 2 times k prime is equal to, well, they have a common factor, right? I can factor that out. 2 times k plus k prime, right? Now I'm going to let t equal k plus k prime. Now, one little assumption I've made in my proof that you probably didn't catch on to that I've made a presumption about is that if I add 2 integers, I end up with another integer. So that I'm making, I know that as in fact a mathematical truth about integers. So I think that's perfectly safe to do. So if I have t and I assign it to be k plus k prime, what should t be? It's an integer, right? It's an integer. Then m plus n is equal to 2 times t, where t is an integer. Where t is an integer, right? Piece of cake. Therefore, are we done? Yeah, we're done, right? We just showed that m plus n is equal to 2 times another integer, but that's even, right? So let me just summarize that. Therefore, by the definition of even, m plus n is even. And we're done. Bam! We did it. Okay, so those are 2 examples, one with existential, one with universal. I'm going to show you an example of this proof by division of cases, because I promised I was going to, I mentioned it, and I thought, well, that's kind of interesting to bring that up, so let's talk about that. Let's do an example of that. Okay. This claim is going to look a little strange at first, but I assure you it is quite nice and simple. Here's the claim. Any two consecutive integers m and m plus 1 have opposite parity. So if you're wondering what I mean by this, so this is the example I was mentioning earlier. If I give you m and it's even, my claim is that m plus 1 is odd. And if I give you m is odd, then it should be that m plus 1 is even. That's the claim. For you, this might be an obvious thing, but in mathematics, we have to be careful. Obvious is not an excuse to not justify it, okay? So words like it is obvious or it's obvious are not really mathematically tenable terms if you want to justify for somebody that something is in fact true. Instead, you could explain it to them. So if it's not obvious, you can write it in words and explain it to them. Hopefully I'm clear about that. So let's prove this claim. So I'm going to show you how you can do this with this case-based approach. Let m be an arbitrary integer. Then m is either even or odd. Now, to be clear, somebody might say, Dan, technically this is a claim that you would still have to prove, but we know that this claim is actually true. I'm just going to assert this as a fact, but there is actually a theorem out there that you can use to actually prove this from number theory, but I'm not going to prove that for you. I'm sure for this audience, this should be it's clear, right? It's something that you can see quite quickly. Okay. So I'm going to decompose this into two cases because m is either going to be even or odd. So I'm going to have two cases. So case 1, m is going to be even. So m is even. In this case, what does that mean? How do I prove it when it's even? I would use the definition of what even is. I use existential instantiation to get a name for an integer because this will exist in this sense. In this case, m is equal to 2k for some integer k. There's some funky noises in the back. For some k. And so, what's m plus 1 then? If m is equal to 2 times k. What is it? M plus 1 is then equal to 2k plus 1. And is odd by definition. Hence, m is even, and m plus 1 is odd. So that's case 1. So notice that by decomposing this into two cases, I can make more assumptions about what m is. This is often a very handy technique. When you're trying to prove claims directly about algorithms, you'll very often find that you might need to use this decomposing into cases because there might be two possibilities that could happen during execution, for example. This is something that you should be aware of. Or at least I want to make you aware of that fact. Okay, so case 2. What's case 2? Now you're going to see this is nice and simple. I'm just going to assume m is odd now. Then m is going to be equal to 2 times k plus 1 for some k that's going to be an integer. So what am I going to do? I'm just going to see what happens when I add 1 to it. So m plus 1 is equal to 2 times k plus 1 plus 1, which is, of course, going to be what? What is it? Well, this is 2k plus 1, which is 2k plus 2, right? 2k plus 2 is, so 2k plus 2. You notice there's a common factor of 2 here. So I'm going to factor that out. End up with 2 times k plus 1. Notice k plus 1 is an integer. It's an integer. So what does that mean? So 2 times k plus 1 is what? It's even. It's 2 times some integer. Right? It's nice and simple. Is even. And boom, there you go. And now we need to conclude. We have to conclude our statement here. So now we've considered the 2 cases. Therefore, regardless that's we'll say regardless. It's sort of melted. Regardless of the parity of m, integers m and m plus 1 have opposite parity. And we're done. We've proven the claim. So notice how useful when we decompose it into cases, we can make more assumptions about what m is, but we rely on the fact that we've decomposed it into a complete listing of all the possible cases. So notice that I couldn't just prove this part. I have to prove that it's even or odd. So as a remark, I want to talk about how you disprove a universal statement. Now, remember, I talked about this actually earlier. I talked about with the example of somebody wearing a red shirt. So we're going to talk briefly about how do you disprove a universal claim. So what did I do in that example I mentioned? If somebody claimed to me that all my friends were wearing a red shirt, I would point out one of them that was not wearing a red shirt. We have a special name for doing this. To disprove a universal statement, this would be what we would call a counterexample. So I present you a universal claim. Your job is to refute it by presenting a single counterexample. So to disprove universal claims, you must present some counterexample. So you have to present at least one counterexample. So counterexample. That is show there is at least one x in my domain that does not have the property. Okay, so what does that mean? What does that mean? So I'm going to give you an example just to illustrate this idea. So I'll give you a statement. So remember, if it seems really complicated, it's really not. Don't worry. All I'm saying is, if somebody tells you all your friends are wearing red shirts, and you know for a fact that they aren't, all you have to do to demonstrate to somebody that that not everybody's wearing a red shirt, you just point at one of your friends and say, "Hey, he's wearing a blue shirt." So imagine I give you a claim like this for all x, y that are real numbers. If x squared is equal to y squared, then x is equal to y. So suppose I give you this claim here. Now, I can think about how I would prove it, but I can see that there's a problem with this. So what I'm going to do is I'm going to present a counterexample. Now, normally when you present a counterexample, you don't just present the counterexample itself. You present it and then you show that it doesn't have the property. So it isn't just like, oh yeah, this is the thing and that's it. You notice that for example, my existential direct proof that I did earlier, I actually presented to you an example. I have at least one with the property, and I explained to you why it was that thing. It had that property. Same idea here. So I'm going to let x be equal to 1 and y equal to -1. So this is going to be an instance of my counterexample. So these are x and y. Those are x and y in the claim. And I'm going to check that these work to refute the claim. Then x squared is equal to 1 squared, which is equal to 1. And y squared is equal to 1 squared, which is equal to 1. So x squared is equal to y squared, right? 1 is equal to 1, right? Trivially. It's identity. But what does that mean? But x is not equal to y, right? See, 1 and -1 here. Since 1 is not equal to -1. Therefore, the given statement is false. Since I'm not proving anything, I don't usually put the box there. I'm not proving anything. I'm just refuting a claim. So that's really all I have to say about direct proofs. So hopefully you had a little bit of fun with this. This is some fun number theoretic examples. The next technique I'm going to show you is the so-called indirect proof. So in a direct proof, what I did was I used observations or previously established results, usually following from definitions, for example, or observations I can make about the structure of an object to conclude or infer logically claims. In this, you're going to notice that the name indirect, so I'm going to be talking about indirect proofs. I'm going to be showing you one such example of an indirect proof. This is not the only one, but this is most certainly going to be one that you're going to encounter in your study. So one thing I need you to note is that statements in logic are either true or false. So we're restricting ourselves to statements that look like this. Either you can say it's true or it's false. That's what a statement will be in the context we're talking about, okay? We're not talking about ambiguous things. We're talking about very clearly defined terms, clearly defined statements, and we're only restricting ourselves to statements that are either true or false, okay? So if you don't have a logic background, don't worry. Just follow the big ideas. So I'm going to change that period to a comma. So we're going to use this. So I'm going to show you one technique of indirect proof. It's so-called the proof by contradiction. So I'm going to give you a sketch of what a proof by contradiction looks like. It's going to work like this. Now, I should point out that a contradiction is a statement that is it's false for any truth assignment. So if I give you statements that are like, okay, I give you true and true for two valuations of a statement, it's going to be false all the time. This is in contrast to a tautology, which is a statement that is always true, regardless of the truth assignments of a logical form that I decide the sentence is going to be. Anyways, I'm not going to worry too much about the logic side of this. I just want to give you an idea of this. So a contradiction is definitely a statement that's always going to be false. That's the big idea here. So I'm going to be trying to derive a contradiction. So I'm going to make a bunch of nonsense. So the first thing you're going to do in such a proof is you're going to suppose that the negation of the statement is true. So we're going to start by just supposing or assuming that the negation of the statement is true. So if I have a universal statement, I'll make an existential statement. If I have something else, I flip the logic. Basically, I just get a negation of it. So I just presume that the thing that it isn't is in fact true. So the negation of it. Why? So if I'm trying to prove that the original statement is true, if I can do that, if I suppose the negation, and I show that there's actually a contradiction, if I do that, that means it's going to be false for any assignment of the logic. That means that the original statement has to be true, right? So because statements are either true or false. That's at least the idea. So we're going to show this assumption or a supposition if you really don't like assumptions. Leads logically to a contradiction. So a statement that's always false. Then you just conclude that the statement to be proved is true. So the whole idea is you start off by assuming the negation of the thing you want to prove, the statement. Then what you're going to do is you're going to follow the line of reasoning from that. So you're usually going to invoke definitions or a property that you might want to use based on the assumption of the negation. And by doing that, you're going to try to construct something that makes absolutely no sense or something that could never happen. Or it violates the original assumption, just in simple terms. So if we violate the original statement, that means that it and the negation clearly can't coexist with one another of the assumption. Anyways, I'm going to stop saying too many more things. I just want to get us right to the meat and potatoes of this. like I'm saying, there's a lot of ways you can yield a contradiction. So let's do an example. There is no integer that is both even and odd. I told you I was going to give you some weird statement that you would think would be kind of obvious. So here's the claim. There is no integer that is both even and odd. So what do we do based on this sketch? So if I'm saying there is no integer, that means like there is no such thing, right? That means it's a universal statement. So what does that mean? It means I'm going to negate the statement and I get an existential statement. But what is the existential statement? Is that it has the property that it's both even and odd, right? That is. Sorry. Let's suppose not. Just for those that like suppositions over assumptions. I often like to write assume otherwise, but just for the sake of things, I'll say suppose not. For those that like suppositions. Suppose not. And then what you do is you elaborate on this. Suppose not. That is. Suppose there exists n, which is an integer, right? That is both even and odd. That is both even and odd. It follows that both of the following properties hold. Now remember, n is both even and odd, so I'm going to just use what I did before in my previous examples. I used an existential I'm getting really excited. I used an existential instantiation to create two names, and I'm going to use them to try to derive a contradiction. So watch this. Watch this. So it follows that both n is equal to 2a for some a, which is going to be an integer, n is equal to 2b plus 1 for some b, which is another integer, and the following. Now remember, n is an integer, right? So it can't be that like this equals something and then that equals a different thing. They have to be equal to one another because it's n, right? And that 2a is equal to 2b plus 1. That has to be true, right? Because it's n. N is equal to n. Gotta bring it back. So anyways, we know that, so remember, we know that n is equal to 2a, and n is also equal to 2b plus 1. So as I mentioned on the previous board, we know that 2a is also equal to 2b plus 1 because n is equal to n, right? That's just identity. So I'm just going to simplify things down a little bit by simplifying this equation here. So by simplifying, we get 2a minus 2b is equal to 1, right? I'm just going to subtract off. I'm going to subtract both sides, 2b. And then this is true if and only if. This is abbreviation for if and only if. Some people also use the double arrows like this. If and only if 2 times a minus b is equal to 1. Now I can rearrange this, and a minus b is equal to 1/2. Now, one important property I already mentioned earlier about integers is that if you add 2 integers, you get an integer. As a byproduct of this, if you subtract 2 integers, you should also get an integer. So over there, that looks a little suspect over there. So let's see what happens. The difference of a minus b, must be integer. As a and b are integers, right? Are integers. However, a minus b is equal to 1/2, and 1/2 is not an integer. What is it? It's a rational number. It's not an integer. Therefore, a minus b is both an integer and not an integer. Which is a contradiction. And naturally, you would say, therefore, you would say a statement. But typically, contradiction proofs, the convention is that you don't normally write that after, because you just said what the contradiction is. And because it's a contradiction, that means that the original statement must be, in fact, true. Because if you take its negation and it leads you to a contradiction, remember, is a statement that's always false, then it means the original statement must be true. Okay? So that's why we call it an indirect proof. Okay. Now it's worth noting that I am not going to show and talk much about it, but there's another type of indirect proof called a proof. It's called proof by contraposition. This is another one that takes advantage of the form of a certain set of logic. So if you give me a statement, I can give you its contraposition or contrapositive to be positive. Sorry, I'm getting a little excited. If I give you a statement involving a conditional, I can give you something called the contrapositive. I can take such statements and I can do some neat thing with them. I just want you to be aware that this exists. I'm not going to do any examples with it because it's a little bit more technical. I think that this is more intuitive to talk about. Just remember, the big idea with proof by contradiction is that I assume or suppose the negation of the statement, and then I try to show that the statement yields a contradiction. Now, it doesn't have to be as garbage or contradictory as this thing, but it might be that it violates the assumptions that you start off with, for example. In an algorithm, this is quite common. So, for example, you might end up having something where you're supposing that you have an answer that an algorithm outputs, but you assume that it doesn't actually do that, so that must exist another answer that pops out of your algorithm. And what you do is you follow through properties that your algorithm has, and you can show that you can take such an answer, you can actually constantly improve it, so you actually get an answer that looks exactly like the one the algorithm gives you. But if you suppose it didn't exist, you suppose it exists and it's better, but your algorithm's able to build one out of the answer, then it must be that the algorithm produces it, hence a contradiction, and so on. So this is actually something that does pop up when you do analysis of algorithms and you try to prove the correctness of some algorithms. This typically pops up, this structure I just talked about, pops up oftentimes when we deal with optimization problems. But I'm not going to go into too much detail there. Clearly I get really excited, so I'm going to avoid doing that because I got to keep things ground and pounded in mathematical, that dreaded M word, the mayonnaise. Okay, so I just want to make sure I got everything here. Okay. So anyways, this is the last bit of this that I'm going to be covering. So I'm going to be covering a topic called the principle of mathematical induction. So you may have seen this before. If not, hopefully this will help enlighten you on what it's about. We're going to talk about the principle of mathematical induction. I'm going to do a couple of examples after I state what the principle of mathematical induction is. Oftentimes this gets abbreviated as PMI or MI. So I'm going to recall the following theorem. So this is going to be the principle. So this is the theorem that I'm going to give you. This is principle of mathematical induction. Sometimes we'll call it PMI or MI. I think I call it MI in the notes. So I'll just stick to that at some point. So the principle of mathematical induction is as follows. Let S of n denote a statement regarding an integer n. And let b, which is going to be another integer, be fixed. So when I say fixed, that means it's a constant. So it's something I've fixed. So for example, if I have a piece of paper and I have a tack, this piece of paper can exist and be out in the air wherever. And I fix it, I'm using a tack to pin it onto a board. So it can't take on another position. It's on the board. Hopefully that's clear. So when I say fixed, it's not arbitrary anymore. I can assume that it's arbitrary and then I can fix its value. But the point here is that it's going to be fixed. It's some constant that's going to be a part of how I invoke PMI. So if the following two conditions. So here's two conditions here. If S of B is true, and for every k greater than or equal to b, it's that if S of k, if S of k, then S of k plus 1. So this is a conditional statement. So if, for example, so what we'll do is we'll show that S of k is true, then that S of k plus 1 follows from S of k. Then then for every n greater or equal to b, the statement S of n holds. This is a very important theorem. Sometimes people call this weak induction, if you're curious. This is in the contrast to things like strong induction or double induction. There's very different kinds of inductions. But this is the classic weak induction, the principle of mathematical induction, or mathematical induction, some people say. So I just want to give you the intuition with mathematical induction. I need a cat. Somebody bring me a cat. I need a cat. I need a cat. Just to explain the intuition behind mathematical induction. Okay, so I want you to imagine, here, give me that. Excellent, thank you. Okay, so I want to imagine I have a cat, okay? So I want to teach this cat how to climb a ladder. So I have this lovely cat. Say hi to Mochi. So what's going to happen is I'm going to start Mochi at some step. So I'm going to first show Mochi how to climb up one step. So that's like S of B. Now, I would love to show Mochi how to go to S of B plus 1, S of B plus 2, S of B plus 3. But there's a lovely mechanism in the principle of mathematical induction that allows me to do this. Notice that for every k greater or equal to b, if S of k, then S of k plus 1. So if I show S of k was true, and now remember, k was b when I start, and if I show that S of b implies S of b plus 1, and S of b plus 1 implies S of b plus 2, and so on, I can show Mochi how to climb up the entire ladder, one rung at a time, using the arbitrary step of step 2. So that's why and how we can use mathematical induction. Mochi's starting to get impatient with me. I better go take her and put her down, okay? Thank you, Mochi. It was fun having you here. So anyways, very hairy. So anyways, the whole idea here is that I start off at a statement I can easily prove for you, and I show you how you can go from one rung in the ladder to the next rung, so that when I finish, I can go from any rung to the next rung, completing the entire lesson of climbing up the entire ladder for Mochi. Okay? That's how we use mathematical induction. It's very nice and powerful, and it comes up with nice and clever and simple proofs. Sometimes. But oftentimes it seems like it gives you a lot of power to work with. I'm not going to prove PMI here for you, but I'm going to use a couple of examples to illustrate how you can use the principle of mathematical induction, okay? So I want to start off actually and motivate a very basic example, and this is one that I showed you at some point. If not, you will be seeing it now. So I'm going to consider, consider the series, the sum from I is equal to, let's go, I is equal to 1 to n of I, which you might know this as me saying that's 1 plus 2 plus 3 plus 4 plus ... plus n for any n greater or equal to 1. So this is the arithmetic series, right? So what I'm going to do is I want to find a nice closed form expression for this sum. Now, you might know it, but I want to motivate how we can get it, okay? So I'm going to start off by just trying to find a pattern. So when I check n is equal to 1, what happens? So this is just 1, right? So it's 1 to 1, which is just 1, right? When n is 2, it's 1 plus 2, which is equal to 3. When n is equal to 3, it's 1 plus 2 plus 3, which is equal to 6. and so on. I can go to n is equal to 5 if you really want me to. 1 plus 2 plus 3 plus 4 plus 5, and that is 15, I believe. So I want to think about where I can get an idea of how this works. Now I want you to look at this kind of carefully here. I'm going to draw a picture, and I'm going to try to encapsulate what I'm trying to do over here, to try to find a pattern. Okay, so when I start off with 1, I want to imagine it like a box. Okay, when I have 2, I want to imagine it like I have 1 plus 2. 1 box, then 2 boxes. When I have 3, I want you to notice that it's like I have 1 plus 2 plus 3. It's like each one is sort of one beyond the next one. It's comprised of the other one. Now, you could analytically use this relationship to derive a closed form if you really wanted to go bonkers. Instead, I'm going to do something that's going to look a little strange at first, but once you see it, you'll see it really well. So I'm going to have 1, 2, 3, 4, 5. Okay. So I would like to have some nice way of expressing this. Now, right here I have 5, right? There's 5 towers here of blocks. I have 5 towers of blocks. I would love to know a nice simple formula to calculate how many boxes I have here. Now, this is where the mathematical intuition really kicks in, and where your pattern-seeking abilities might help you or they might damn you. So, I want you to notice something neat here. Okay. So, what if I was able, because I know this dimension here. I know there's 5 here. I know there's like 5 here, right? But you'll notice it doesn't quite, like if I were to try, because I want you to really go back. Go far back in your intuition about how you calculate things. Think of like area, for example. You would agree with me that if I drew this as a complete box, that if I knew the boxes that weren't there, I knew how many there were not in my current set of boxes, I can calculate the area of all the boxes, which would determine for me the number of boxes, if I'm counting each one as an individual unit. Now, you might intuitively think to fill this in and try to calculate it out that way. I'll do you one better. This is where that intuition sort of pays off. Let me get a different marker. I'm going to start off up here. I'm going to draw a box like this to complement the other one. And then I'm going to, for this one, I'm going to draw a box, a set of boxes that's going to fit into the other box, set of boxes. Sorry. Getting really excited about this. So notice that instead of trying to fit a box, instead I'm going to try to complete the box by creating a second box that is the mirror image of it. So now notice that, like for 3, I could do this. And for 5, I could do this. So I want to get you some intuition before we try to prove the thing. Because you want to try to guess a good closed form. Try to guess a good closed form. And if you can guess a good closed form, then we might be in business to actually prove it with mathematical induction. Because mathematical induction doesn't give us the answer. It's a mechanism we can use to check our guess. So if you see what I'm saying right now, you have this 5. What's the dimension on this side? It's 6, right? So it's 6. So we have 5 times 6. And if I wanted to compute the area of all the block squares, like if I assume they're all individual units, how would I do that? Well, you notice it's exactly half of this area, right? It's exactly half. So we have 5, 6, and it should be half of this, because I constructed the other box to be literally the exact same number of boxes, just flipped. So what's a good guess for this? So here's a good guess, maybe. So if I want to say it in terms of n, what would that be? It'd be, that's n. That's n plus 1. And I want half the area of that box that I've just constructed with the green and the black. And so that's my guess. And if you guess this, you'd probably be correct, because it is correct. And we need to now check that it's in fact correct. And we're going to use the principle of mathematical induction to do this. So here's the claim we're going to prove. Claim for any n, let's see, positive integer, the sum from I is equal to 1 to n of k is equal to 1 plus 2 plus up to n times n plus 1 over 2. So, just as a reminder, I need another cat. As a reminder, I'll come right over there. Remember, we have two parts to our proof of mathematical induction. We have a base step and the induction step. Okay. So what we're going to need to do is we have to first demonstrate S of b. So we got to figure out what b is. Naturally, the b would be the smallest value we can take on. Naturally, b will be the one that we'll take on. Everybody say hi to Miss Kitty. Miss Kitty does a pretty cool dance. Look at her. So Miss Kitty, we have to show Miss Kitty how to take the first step up the ladder. So we're going to demonstrate the smallest value for n, which would be naturally 1, right? So we're going to show Miss Kitty how to show and climb up the first rung. And then we're going to use the induction step to show Miss Kitty how to climb up any arbitrary step. And if Miss Kitty knows how to climb up the first step, then she can use that to climb up the second step, then the third step, then the fourth step, then the fifth, and so on for any n. Okay, so that should make the claim pretty darn clear. So we're going to use that strategy. That's the game plan. So the first thing I'm going to do is I'm going to denote a statement in the form that I would like to induct on. So I have to decide a variable I'm going to do for the induction, some integer. So for any integer n greater or equal to 1, let S of n denote the statement. Denote the statement S of n, which is going to be the sum of I is equal to 1 to n of k. We'll go with, do I have k's or i's? I think I have i's. So let's go with, let's go with I. I was getting excited. I was going to put k. Let's go with I is equal to n times n plus 1 divided by 2. So that we're going to denote that as the statement that we're going to try to prove. And now n is what we're going to perform the induction on. So we're going to vary what n is in the manner we described for Miss Kitty. So we're going to have our base step first. Now it's worth as a remark that you can do as many base steps as you like to get up to the value you need for the induction step to work. For our case, it's going to be rather straightforward. So I'm going to have a base step. I'm going to have when n is equal to 1. So I have to show for S of 1 that S of 1 is in fact true. Then S of 1 is the sum from I is equal to 1 of I, which is exactly equal to 1 plus 1, 1 times 2 over 2, which is equal to 1. both sides of the equation, are equal, so S of 1 is true. Bam. That's the base step. Like I said, if you needed to make n higher up to show Miss Kitty how to do the next do any arbitrary step, you would make more base steps, okay? Now we're going to show the induction or inductive step. I'll just call it the inductive step for the sake of consistency, if I would like to call it that. So I'm going to have S of k, so I'm going to just remind you what I'm going to be showing. I'm going to be showing that if S of k, then S of k plus 1. So I'm going to assume S of k, and I'm going to show you how S of k, if S of k, then S of k plus 1 will follow from it. So we're going to take advantage of that structure. If you don't like Miss Kitty climbing a ladder, think of a bunch of dominoes. Just you nudge the dominoes, they all fall over. Why? Because I started off by pushing one of them. So one important thing I'm going to do is I'm going to fix another variable as I did in the statement of the theorem. So I'm going to fix some k greater or equal to 1. The reason why it's 1 is because b was 1. So if you're wondering what b was fixed as, b is equal to 1 here. So we're going to assume that S of k, which is just going to be the sum from I is equal to 1 to k of I is equal to k times k plus 1 all over 2, holds. Now I'm going to call this right here, this idea, I'm going to call this the inductive hypothesis, or the induction hypothesis. I'll initialize it as IH, so whenever I need to use this, I will use it. The whole strategy here is I'm going to try to use S of k. I'm going to invoke S of k to derive S of k plus 1. To be proved is that S of k plus 1, which is the sum from I is equal to 1 to k plus 1 of I is equal to k plus 1 times k plus 2 all over 2 follows. So notice I stated what S of k is. I stated what S of k plus 1 is. So now I have my game plan. So beginning on the left-hand side. So the whole idea here is I'm going to take the left-hand side of S of k plus 1. I'm going to do some fun algebra to derive the right-hand side of the S of k plus 1. And if I can do that using S of k, then I'm done. And once I've done that, I can invoke the principle of mathematical induction. And the claim will be then proven. Okay? So beginning with the left-hand side, of S of k plus 1, we have the sum from I is equal to 1 to k plus 1 of I. Now, remember, the strategy here isn't to just try to simplify this as much as you can. Remember, we cannot just conclude the right-hand side from this. We have to start with the left-hand side. We're going to use S of k to get the right-hand side of S of k plus 1. So the whole idea is I'm going to do what I suggested near the beginning of this when I was trying to look at those patterns. I'm going to try to expose a property that relates to the previous value of n, which we've fixed as k here. Okay? So let's head. So notice that I'm going to use the strategy that I'm going to do is I'm going to relax or massage the summation into something that looks like something I want. So I'm going to write the final term, which would be when I is equal to k plus 1. And I'm going to add, I'm going to rip that out of the sum from I is equal to 1 to k of I. But what's this? What's this? What's that? That's S of k, right? That's S of k. But this is equal to k plus 1 plus k plus 1 times, k times k plus 1 all over 2. This is by the induction hypothesis, S of k. Remember, I just need to show Miss Kitty how to go from one rung to the next rung. Just like Mochi earlier on. Mochi was a little grumpy near the end of that. So all I'm doing is I've shown, so me doing this right here is just like showing and taking Miss Kitty from that current rung to the next rung. That's all I'm doing here. So I'm invoking the induction hypothesis. And now I'm going to simplify this down. I'm going to make a common denominator. So I have 2 times k plus 1 plus k times k plus 1 all over 2. And I'm going to expand this all out. I end up with 2k plus 2, so 2 times k, 2 times 1, plus k squared plus k all over 2. We simplify this down, and we end up with k squared plus 3k plus 2 all over 2. But what's this? If you know your factoring rules, let's say your FOIL or something like that, you can simplify this down a little further. You end up getting k plus 1 times k plus 2 all over 2. I'll let you think about that. Thus, one arrives at the right side of S of k plus 1, and S of k plus 1 is also true. This is completing the induction step. So the induction step or inductive step is done. Now I need to, because I have the base step and the inductions or inductive step. Those are the two things I need to invoke the principle of mathematical induction. Therefore, by mathematical induction, the statement S of n is true for all n greater or equal to 1. And we're done. Bam! We did it. So note that the reason why I wrote S of n as opposed to the statement is because I was kind of running out of space here. If you really wanted to, you could write out the full statement right here. That's usually ideal, because that's your actual conclusion. But if you're running low on space, S of n, we already gave it a symbol and it has a name. So it's perfectly fine. So hopefully this is all right. We're going to do one last example, just showing another example of principle of mathematical induction. I'm going to come back to our friend factorial. Okay. So we're going to prove the following claim, okay? Let's do this, everybody. So let's do this. So I'm going to prove the following. So here's the claim. For all integers, n greater or equal to 4, 2 to the power of n is strictly less than n factorial. Now, just as a reminder, n factorial is equal to n times n minus 1 times n minus 2, all the way down to 2 times 1. That's factorial. So we're going to prove this using mathematical induction. So what we're going to do, how do I start the first one? How did I start my first example? How did I do that? What did I do? I denoted a statement. So let's do that. For any integer n greater or equal to 4, I chose 4 because that's in the statement here. Denote b of n as b of n, where we say 2 to the power of n is less than n factorial. We're going to use that statement. So we're going to induct on n. So what am I going to do? I'm going to first have my base step. Now remember, the statement is for n greater or equal to 4. So we have to be careful when we're doing this. We're not just starting at 1, we're starting at 4. So my base step is I'm going to have n is equal to 4. Now, the great thing is that n is 4 is something I could easily evaluate for this statement. So I just want you to recall back to your powers of 2. Since 2 to the power of 4 is equal to 16, is less than 24, which equals 4 factorial. I don't want to use n, I'm calling n 4 at the moment. This inequality holds. So b of 4 holds. Now we're going to do the inductive step. The reason why I wanted to show you this example is because it's a little different than the other one. I'm going to use the induction just slightly differently. So I'm going to show that if b of k, then b of k plus 1. So I'm going to fix some k greater or equal to 4. I'm going to assume b of k to the power k less than k factorial holds, which is just the induction hypothesis, right? Remember, we're going to use this induction hypothesis to derive b of k plus 1. So we're going to use this as a chunk. So we're going to start, remember, we want this like a rung, just like when we have Miss Kitty or Mochi. We want to help Mochi or Miss Kitty climb up that next rung for any arbitrary rung of the ladder. But we have to start off at one rung before we can get to the next one. Miss Kitty can't just like magically fly up to the rung. You've gotta start somewhere. This little cat just can't seem to jump up high enough. You've seen really cute Miss Kitty, right? Miss Kitty just needs that little delicate jump up there. Okay, so we wish to show that b of k plus 1 also holds. b of k plus 1 states b of k plus 1 to the power k plus 1 is less than k plus 1 factorial, right? So we're going to start off again with the left-hand side approaching the right-hand side, but I'm going to just do it in a slightly different way. I'm just going to observe a property of exponents. Let us consider the left-hand side. And I'm talking about the left-hand side of b of k plus 1, if you want to be more precise, or exact if you want to use that terminology. Observe that 2 to the power of k plus 1 is in fact equal to 2 times 2 to the power of k, right? We know this because it's the property of exponents. Let's use this to finish up the proof, okay? So how can we use the induction hypothesis then? We know that 2 to the power of k plus 1 is equal to 2 times 2 to the power of k. Look what b of k has. 2 to the power of k is less than k factorial. So I'm going to use that fact because I have 2 to the power of k sitting on the right-hand side of that equation right there, right? So let's do it, okay? There we go, perfect. By the induction hypothesis or inductive hypothesis, IH, 2 times 2 to the power k is less than 2 times k factorial, right? That's what it says. I just extracted out that extra 2. So now we just have to deal with that. Then 2 times 2 to the power of k is less than 2 times k factorial. Now, there's a little bit of a finesse to this, and this step is a little tricky when you first think about it. Okay, what's k? Is k like 3, 4, 5? We know that k is at least 4, right? But that's a 2 right here. What I would like to do is replace this 2 with something that looks like a k. But not just any k. I want to make it so I can form k plus 1 factorial, right? But I know for a fact that k is in fact at least 4, right? So I can indeed write the following, which is less than k plus 1 times k factorial, right? As k is greater or equal to 4. Well, what's this? What's this? That's the diff. I could rewrite this in terms of factorial. This is k plus 1 factorial. Thus, b of k plus 1 follows. Boom, we have the base step and the inductive with the inductive step. What can we say now? What can we say? We can use the principle of mathematical induction. Therefore, by mi, for every n greater or equal to 4, b of n is true. And we're done. Boom! See? Mathematical induction can be easy, right? Just remember, think of the cat trying to climb up the ladder. We have to show the cat the first rung, then the next rung, but we have to show the cat how to climb up any arbitrary rung. And if you can do that, we can complete the entire trip up to the top of the bunk bed. Okay? So that's really everything about mathematical induction I really have at this time. So anyways, I think that's everything I've got here. I have a lot of fun notes in front of me. This is everything I got here. So it was a pleasure to have you down, and hopefully this little bit of mathematical primer will help you in your studies. So that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.